Today we continue our discussion on velocity and acceleration analysis of planar mechanisms through the use of velocity and acceleration diagrams. Before we take up a little more complicated problem of velocity and acceleration analysis, I would like to develop a very useful concept involving the so-called Coriolis acceleration. Very often we find in mechanisms one point of a rigid body, say number I, is constrained to move along a given path in another moving rigid body, say number j. In such a situation, it will be useful to consider instantaneously two coincident points, one belonging to the first body, that is I, and the other in the second body, that is number j. In such a situation, as we shall see, that one component of acceleration which is not trivial becomes very important. Consideration of that particular component, which we call Coriolis component of acceleration, is very important. Let us consider two rigid bodies shown in this figure, namely number 2 and number 3. As we see that there is a slot in this body number 2, and there is a pin in this body 3, the center of which is always constrained to move along the slot. So we consider two rigid bodies, namely number 2 and 3. We consider instantaneously two coincident points, say P2 and P3. At this instant, P2 and P3 are coincident, but P2 belongs to body 2 and P3 belongs to body 3. This is the configuration of these two bodies at say time instant t. After some time delta t, that is at t equal to t plus delta t, the body 2 which is moving has taken up this configuration. From here at time t plus delta t, body 2 has taken up this new configuration and it has rotated through some angle, it has moved through some distance. The body number 3 has also moved, and the center of this pin in body 3, P3, has currently this location, which is P3 prime. And the point P2, which belongs to body 2, that is a point on this center line of the slot, has come here, which I call P2 prime. So P2 and P3 are the two instantaneously coincident points, P2 belonging to body 2, P3 belonging to body 3. During time delta t, P2 has moved to P2 prime and P3 has moved to P3 prime. So if we want to find out the velocity of the point P3, as we see, the displacement of the point P3 during this time delta t is given by the vector P3 to P3 prime. So if I say delta s, that is the displacement of the point P3, is equal to the vector P2 P2 prime. The point P2 has gone from P2 to P2 prime. This vector, that is the displacement of the point P2 plus P2 prime P3 prime. This vector P3 P3 prime is P2 P2 prime plus P2 prime P3 prime. This vector, the vector P2 prime P3 prime. Now if we think of an observer who is sitting on body 2. If we ask this observer who is attached to body 2, what is the displacement of the point P3, then his answer will be the point P3 at time t was here and now it has moved to P3 prime. So, this P2 prime P3 prime is the displacement of the point P3 as seen by an observer sitting or attached to body 2. So, this is the notation we use, delta P3 stroke 2, which means that is the displacement of the point P3 as seen by an observer attached to body 2. Now, if we divide both sides of this vector equation by the time delta t and take the limit as delta t goes to 0, we get velocity of the point P3 is velocity of the point P2, these are the absolute velocities of the point P3 and P2 respectively, plus velocity of the point P3 as measured by an observer sitting on 2. So, this is the relationship between the velocities of these two instantaneously coincident points, namely P2 and P3. Common sense intuition might suggest that a similar relationship will also hold good for the acceleration of these 2 points, that is, acceleration of the point P3 is acceleration of the point P2 plus acceleration of the point P3 as measured by an observer attached to body 2. However, this is wrong. This is not correct. In fact, we get another term which is twice of omega 2 cross Vp3 2. It is this last term is called the Coriolis component of acceleration. So, let me repeat, by considering 2 instantaneously coincident points P2 and P3, where the path of the point P3 in body 2 is known, that is along this center line of the slot, Vp3 is Vp2 plus Vp32, whereas AP3 is AP2 plus AP32 plus the Coriolis component of acceleration, which is twice omega 2 cross Vp32. Now, this Vp32 and AP32 are nothing but the velocity of the acceleration, velocity and acceleration of the point P3 as measured by an observer who is sitting or attached to body 2. Now, velocity of the point P3 as seen by this observer on body 2 is always tangent to the path. If the path is known, then Vp32 is tangent to the path. But AP32 have 2 components, one tangent to the path and the other normal to the path. The component of the acceleration AP32 along the normal to the path we already know is AP32. If I take the normal to the path, this component is Vp32 squared divided by the radius of curvature of path at that instant. That is the normal acceleration, as we know, v square by rho, where rho is the curvature of the path. All these relationships will be very useful for kinematic analysis of mechanisms, where we will see that one point of a rigid body is constrained to move along a slot or along a given path in another moving rigid body. We have not proved why this Coriolis component of acceleration comes. However, I will take a simple example to demonstrate the existence of this component. To demonstrate the existence of Coriolis component of acceleration, let us again consider two rigid bodies, namely body 2, which is this rod, which is hinged at the point O2, and another rigid body, namely 3, that is this block, which is constrained to move along the rod. So, the path of P3, we can consider two instantaneously coincident points here, which we call P2 and P3. P2 is a point on this rod and P3 is a point on this block 3. P2 and P3 are coincident at this instant. What is the path of P3 on 2? If we fix body 2, I can see the block P3 can only go along this rod. So, the path of P3 on body 2 is this vertical line. It is along the rod. So, Vp32 will be along this vertical line. Let us consider if omega 2 is the angular velocity of this rigid body 2, that is, this rod is rotating counterclockwise, and in time delta t, it rotates through an angle delta theta. During this time delta t, body 3 has moved from here to there. That is, P3 has gone to P3 prime, whereas P2, the point on the rod, has moved to P2 prime because it is rotating about the point O2. Now, if we look for the acceleration of the point P3, we can talk of acceleration of the point P3 along two, by expressing its two components, one along the rod and other perpendicular to the rod. What we see, if we ask a person sitting on body 2, what is the movement of this point P3 prime? Because the observer is always sitting on body 2, he or she thinks that P3 is moving only along the rod. No motion perpendicular to the rod of P3 prime is perceived by that observer. So, what he or she misses is this transverse distance. According to the observer sitting on body 2, P3, the transverse displacement is only this much. But as we see from the figure, the transverse displacement is this plus this. It is this plus AP3 prime which the observer misses. And that, let us calculate what is that. As we see, AP3 prime, this distance, as we see, during this time delta t, the rotation of this rod number 2 is delta theta, and this distance P2 prime to P3 prime, P2 prime to P3 prime, it is the movement of the block 3 along the rod, which is the velocity with which it is moving on the rod, which is Vp3 2 into delta t. During time delta t, it is moving with the velocity Vp3 2. So, this is the movement P2 prime to P3 prime, and this angle is delta theta. So, into delta theta, which is equal to Vp3 to delta t, and delta theta is nothing but omega 2 into delta t, because it is rotating with constant angular velocity omega 2. Even if it is not constant, during time delta 2, due to the angular velocity omega 2, the rotation is omega 2 into delta t. So, this comes out Vp32 omega 2 into delta t squared. So, this extra transverse displacement that the point P3 prime has, which the person or the observer sitting on body 2 misses is given by this. And this extra displacement, as we see, is proportional to delta t squared, which means this is due to some acceleration in the transverse direction which this observer is missing. And what is the magnitude of that acceleration? That is magnitude A Coriolis. What is the magnitude? That is twice of V P3 2 into omega 2, because with this acceleration I can cover a distance half A Coriolis into delta t squared during the time interval delta t, which gives me back this AP3 prime. So let me go through this argument once more. The point P2 has come to P2 prime, and according to the observer sitting on body 2, P3 has gone only from P2 prime to P3 prime. So the transverse direction displacement is P2 to P2 prime. However, as we see, there is an extra displacement in the transverse direction for the point P3, which is given by AP3 prime. And AP3 prime can be covered in time delta t if there is an acceleration in the transverse direction of magnitude twice Vp32 into omega 2. And this is what we call Coriolis acceleration. As a result, we can write acceleration of P3 is equal to acceleration of the coincident point P2 plus whatever acceleration is along the slot which this observer sees for the point P3, that we denote by A P3 2, and the component which this observer misses, which is this A Coriolis, and that we can easily see by looking at the sign of the cross product twice omega 2 cross Vp32. Vp32 is along the slot, omega 2 vector is perpendicular to the plane of motion, and this cross product will give the magnitude of the Coriolis acceleration as this. And this last term is what we call A Coriolis. At this stage, let me consolidate whatever we have seen about these two coincident points. So what we do, we identify two bodies, namely body number say I and body number j. That is link number I and link number j. Suppose it is the path of a point in body j, a point in body j I call Pj, and it is the path of Pj in body I is known. This is very important. Whether it is the path of Pi in body j is known, or whether it is the path of Pj in body I is known. So here I am assuming the numbering is such that it is the path of Pj in body I, body numbered I is known. Then I can find the velocity of the point Pj is velocity of the point Pi, which is instantaneously coincident with Pj, plus velocity of Pj in I, that is as measured by an observer attached to body I. And this velocity Vpji is tangential to this path of Pj in body I, which is known. But for acceleration, I will have acceleration of Pj is acceleration of Pi plus acceleration of Pj as seen by an observer on body I plus a Coriolis, which is twice omega I, angular velocity of the body I is known, cross V P J I. This I write API plus. There are two components of this APJI. The path of Pj in body I is known. So, this has two components, one normal to the path and the other tangential to the path. The normal component I write APJI, say the normal component n plus acceleration Pji, the tangential component which is tangent to the path, and normal component is normal to the path, plus a Coriolis, which I write twice omega I cross V P J I. After the velocity analysis is completed, as we see, this normal component will be completely determined, because this normal component is nothing but V P J I squared divided by rho of that known path along the normal direction towards the center of curvature, plus other two terms as usual, A P J I T plus a Coriolis, that is twice omega I cross V P J I. As we will see later, that these two equations, one for the velocity and two for the acceleration, will be very useful for carrying out kinematic analysis of planar mechanisms, particularly when one rigid body is guided along a given path in another rigid body. Now, we shall solve a problem to show you the use of these two equations for carrying out the kinematic analysis. At this stage, we consider the kinematic analysis of a slotted lever quick return mechanism, which we have seen earlier. This is the slotted lever quick return mechanism used in shaping machines. In this mechanism, there are 6 links. One is this rotating link, on which, that is link number 2, fixed link is link number 1. This is link number 3, this circular block, which is hinged to body 2 at this point. And this is link number 4, the slotted lever. This is link number 5, and this tool holder or the tool is the link number 6, which has a prismatic pair in the body number 1. Now, as we see, as this mechanism moves, this particular point of body 2 or body 3 is always moving along the axis of this slot in body 4. So, if we call this point, say, A2 or A3, two coincident points, one belonging to body 2, other belonging to body 3, A2 and A3, they always remain coincident. But if we consider a point A4, which is instantaneously coincident with A2 and A3 at this instant, but belongs to this body 4, then A2, A3 always remain coincident, but A4 moves in a circle, but A2 and A3 is moving in a different circle. A4 is moving on a circle with this point as center. So, A2, A3 always remain coincident, but A4, A2 and A3, they have relative movement. A4 is a point belonging to this slotted lever. Now, so that is the concept of coincident points. A2 and A3 always remain coincident because this is the block center where body 3 is hinged to body 2. A4 is a coincident point belonging to body 4, which is going in a circle with this point as center and this as radius, whereas A2 and A3 are going on a different circle. So, they always do not remain coincident, but for the purpose of kinematic analysis, it will be very useful to consider the velocity and acceleration relationships between these two coincident points, instantaneously coincident points, say A2 and A4. So, this is the problem which we will be analyzing now. Suppose the angular velocity of this body 2, that is the bull gear, is given and assumed to be constant. Let us find out at this configuration what is the velocity and acceleration of the tool holder. Let me first draw the kinematic diagram of this slotted lever quick return mechanism. This is the fixed link number 1, this is the bull gear, the input link number 2, this is the block link number 3, this is the slotted lever link number 4, this is the tool holder link number 6, and this link is link number 5, which connects the tool holder to the slotted lever. Let me call this point O2, the point fixed on link 2, this point O4, that is the point fixed on link 4, this point let me call A, and this point let me call B. So, the statement of the problem is the angular velocity of this input link omega 2 is given, and let us assume it to be constant. Of course, even if it is not constant, we can prescribe alpha 2 as well. So, omega 2 given and assumed to be constant, that is alpha 2 for this problem let us take to be 0. And we have to determine the velocity and acceleration of the point B, which is same as the velocity and acceleration of the tool holder, that is link 6. To solve this problem, let me first identify 3 coincident points at this block center. P2 that belongs to link 2, which always remain coincident with point P3, which belongs to the block. P2 belongs to link 2, P3 belongs to link 3, but they always remain coincident, so I can write them to be the same point. We consider an instantaneously coincident point P4, which at this instant is here where P2 and P3 are, but P4 belongs to link 4. We should note the difference that P2 and P3 moves on a circle with O2 as the center, whereas P4 moves on a circle with O4 as the center. Now, it is the path of P2 in body 4 is known, that is along this line O4A. So, the path of P2 in 4 is O4A. So, this is a straight line path. The curvature of this path is infinity. To do the velocity analysis, we start as usual from the input end. So, we know velocity of the point P2 is omega 2 cross O2 P2, which is completely known because the vector O2 P2 is known and also the angular velocity vector omega 2 is known. Now, as we have seen, because the path of P2 in body 4 is known, I can also write Vp2 is Vp4 plus velocity of P2 in body 4. Because P2 and P4 are coincident, we have already shown these relations. Now, let me see in this vector equation what are the known quantities and what are the unknown quantities. Velocity of P2 is completely known, so I know its magnitude and its acceleration. But velocity of P4, I do not know the magnitude, but I know the direction because that is perpendicular to O4 P4, that is perpendicular to this line O4A. So, the direction is known, but the magnitude is unknown. Velocity of P2 in body 4, because the path of P2 in body 4 is along O4A, so the velocity must be along that direction O4A. So, here also I know the direction, but not the magnitude. As we see in this vector equation, there are only two unknowns denoted by these two crosses, so I can represent it by a velocity diagram. Let me try to draw it to some scale. Velocity of P2 is perpendicular to O2 P2. Let me draw by this vector. So, this, as I said, we represent by small letters O2 and P2, representing the vector Vp2. The pole of this velocity diagram also represents the fixed point O4. Now, velocity of P4, I know the direction, that is perpendicular to O4A. So, I draw a line through O4 which is perpendicular to O4 P4 or O4A. So, this vector must represent Vp4 and Vp24 is along O4A, that is perpendicular to this line. So, I drop a perpendicular from P2 to this line. This is perpendicular. So, to satisfy this vector equation, what I determine, this point must be P4. So, this point we denote by P4 because O4 P4 represents the velocity Vp4. So, this vector represents Vp4 and this vector P4 P2 represents Vp24. So, we have reached up to this stage of the velocity analysis. Now, we notice that there are 3 points on this link 4, O4, P4 and A. For O4, I have this O4. For P4, I have this small P4. So, the velocity of the point A, I use the concept of velocity image and draw a diagram similar to this line O4 P4A. I write O4 P4A such that O4 P4 by O4 A is O4 P4 by O4 A. I just replace the capital letter by the corresponding small letters. Here, as you see, O4 P4 A are in one line. So, here also small O4, small P4 and small a are in one line, and the ratio is also the same. O4 P4 by O4 A is O4 P4 by O4 A. So, I determine the point A, and this O4 A determines the vector VA, velocity of the point A. Now, to determine the velocity of the point B, we go as follows. A and B are 2 points on the same rigid body phi. So I can write VB is VA plus omega 5 cross AB. A and B are 2 points on the same rigid body phi, so their velocities are related through this equation VB equal to VA plus omega 5 cross AB. In this vector equation, as we know, velocity of A has been completely determined. I know both the magnitude and the direction. For VB, I know the direction which is horizontal because the point B is constrained to move along a horizontal path due to the prismatic pair between 1 and 6. Omega 5 cross AB, I do not know the magnitude because I do not know the magnitude of omega 5, but I know the direction. It is perpendicular to the vector AB. So I know the direction but do not know the magnitude. For VB, I know the direction horizontal but I do not know the magnitude. So again in this vector equation, I have only 2 crosses, that is 2 unknowns, so I should be able to complete the velocity diagram. For VB, because it is horizontal, I draw a line which is horizontal through the point O2 or the pole of the velocity diagram. And this vector, this is VA, we have already got O4A. VB must be horizontal, so I draw a horizontal line. And omega 5 cross AB is perpendicular to AB, that is in this direction. So through A, I draw a line perpendicular to AB. So wherever this line which is perpendicular to AB must represent omega 5 cross AB. And wherever it intersects the horizontal line drawn through the pole of the velocity diagram determines the point B. And now as we see, VA plus omega 5 cross AB gives me VB. So O2B determines the velocity of the point B, that is the velocity of the slider V6 to the same scale in which this velocity diagram has been drawn. So the velocity diagram is complete. We have shown you the use of the velocity image while locating the point A. We have also shown the use of the coincident points, namely P2 and P4, because the path of P2 in body 4 was known, that was along O4A. At this stage, complete velocity analysis has been done, so I can find all the angular velocities like omega 4 or omega 5, because as we have seen, this vector AB represents this vector omega 5 cross AB. Because AB is known, this vector is known, I can determine the only unknown omega 5. Similarly, O4 P4, this vector is nothing but, if I consider O4 P4, that is the velocity of the point P4, which is omega 4 cross O4 P4. Because I know O4 P4 this distance and I know this velocity, I can also determine the velocity, angular velocity omega 4. Omega 3 is same as omega 4 because there is only a prismatic pair between 3 and 4, so they must have same amount of rotation. There can be only relative translation. So omega 3 is same as omega 4. So this completes the velocity analysis of this 6-link mechanism given the input angular velocity omega 2. Everything else has been determined. And once the velocity analysis is completed, once all these angular velocities omega 3, omega 4, omega 5 are known, we are in a position to start the acceleration analysis. Now we shall carry out the acceleration analysis of the same slotted lever quick return mechanism. The kinematic diagram we had already drawn, and we are saying omega 2 is given, and let us assume it to be constant as before, and objective is to find the acceleration of the point B, that is the acceleration of the body 6, which is a slider. So again we consider the coincident points P2 and P4. Now acceleration of the point P2 is omega 2 squared P2O2, because this point is fixed, so P2 is going in a circle. The acceleration of P2 is towards O2, that is P2O2, the direction, and omega 2 square. If there is alpha 2, then I will have also a transverse component that is perpendicular to O2 P2, which is alpha 2 cross O2 P2. But alpha 2 I have taken to be 0, so this is the total acceleration of the point P2, which is completely known. Now we know, considering the two coincident points P2 and P4, it is AP2, I can write AP4 plus acceleration of P2 in body 4 plus the Coriolis acceleration, which is twice omega 4 cross V P2 4. Now, in this vector equation, let us see what are the quantities which are known and what are the quantities which are unknown. AP2 is completely known from the input given acceleration. AP4 has two components. One is towards O4, P4O4, which I can write AP4. There are two components. One is omega 4 squared P4O4 plus alpha 4 cross O4 P4. These two vectors together decides AP4. Then we have AP24. This has two components. One is AP24 normal to the path of P2 in body 4 plus AP24 tangential to the path of P2 in body 4 plus the Coriolis acceleration, that is twice omega 4 cross V P2 4. Now this is the complete expression for AP2. Now let us see on the right hand side which vectors are completely known and which are still unknown. Because we have already determined omega 4 and P4O4, this vector is known, so both the magnitude and the direction are known. Now alpha 4 cross O4 P4, this is perpendicular to O4 P4, so I know the direction, that is perpendicular to the line O4 P4, but I do not know alpha 4, so the magnitude is unknown. So for this vector the magnitude is unknown, but the direction is known. Now AP24N, that is the path of P2 in body 4, which is the straight line O4A. Because it is a straight path, the radius of curvature of this path is infinity, and this, as we discussed earlier, if we write it separately, AP24N is nothing but V P24 squared by rho along the normal to the path towards the center of curvature. Now, for this particular case, because rho is infinity, because the path is a straight line, the radius of curvature of path is infinity. So, this is rho is infinity, so this is 0. So, this goes to 0. Now, AP24T, that is tangential to the path, because the path is a straight line, the path itself is its tangent. So, I know the direction, this is along the straight line O4P, but the magnitude is unknown. Whereas, the Coriolis component, because we have completed the velocity analysis, we have already determined Vp24 and we have already determined omega 4. So, this quantity is completely known. I know both its magnitude and its direction. So, what we see that in this vector equation, I have one cross here and another cross there. So, there are only two unknown quantities. Consequently, this vector equation can be drawn in the vector diagram. So, we by considering two instantaneously coincident points P2 and P4, we reach this acceleration equation between AP2 and the Coriolis component AP24 and AP4. Because there are two unknowns in this vector equation, let me draw the acceleration diagram, vector diagram. So, acceleration of AP2 is this way, which is to some scale I represent this is O2 and this is P2, which is the acceleration of the point P2. Omega 4 square P4 is completely known, and that is parallel to this line towards O4. So, I can draw to the same scale, let it come up to this point. This I call P4 prime. Alpha 4 cross O4 P4 is perpendicular to this line, but the magnitude is not known. So, I draw a line perpendicular to this, and the point P4 will lie on this line such that O4 P4, O2 and O4 is the pole of the diagram, O4 P4 will denote the acceleration of the point P4. Now, twice omega 4 cos Vp24, this is completely known, and that is perpendicular to this O4A, because Vp24 is along this O4A. Now, let us look at this term, which is the Coriolis component of acceleration, which is completely known. If we go back to the relevant portion of the velocity diagram, what we see that Vp4 is in this direction, O4 P4, which means omega 4 is counterclockwise. And this vector P4 P2 represents Vp24, that is this vector. So, this cross product, because omega 4 is counterclockwise and Vp24 is in the upward direction along O4A, this vector turns out to be perpendicular to O4A and in this direction, in the sense of omega 4 rotated through 90 degree. Now, if I transfer this term to the left hand side, it comes with a negative sign. So, here I draw parallel to this line with the magnitude twice omega 4 cross Vp24. Now, this term AP24 tangential, which is along O4A. So, from this point I draw a line which is parallel to O4A, and this line which we had drawn earlier to represent this vector, these two lines intersect here. So, this point I can call P4. This vector is alpha 4 cross O4 P4. This vector represents A P2 4 tangential, and this vector represents the Coriolis component of acceleration. So, now you see that acceleration of P2, this vector is a sum of 1, 2, 3, 4 vectors, namely this one represented by this one represented by this one represented by this, and the last term represented by this. So, once we determine P4, that means I know the acceleration of the point P4, which is represented by O4 P4. This is acceleration of the point P4. Once we know P4, using the concept of image, I can easily get to the point A, as explained earlier, such that this point I write P4 and this point I write A, such that O4 P4 by O4 A is same as O4 P4 by O4 A, and O4 P4 A lie on the same straight line. So, this O4 A represents the acceleration of the point A. Once we get the acceleration of the point A, then acceleration of the point can be determined very easy, of the point B can be determined very easily. It is just like a slider crank. Once we know the acceleration of the point A and acceleration of the B is horizontal direction, you can find the acceleration of the point B just following the method which I explained with reference to the slider crank mechanism. This I would like to leave it to you as an exercise.